If you are new to the world of large language models, you are not alone. As artificial intelligence continue to transform the way we live and work, understanding large language model has become increasingly important. In this video, we will demystify the complexities of large language models, exploring key concepts, application, and ethical consideration for absolute beginners. So let's get started. First, what is transformer architecture? Now, transformer architecture is a type of neural network used in natural language processing tasks. It is designed to process sequences of words or characters in a sentence while efficiently capturing the relation between them. At a high level, the transformer is composed of several layers that process the input sequence one after the another. Each layer consists of two parts, a multi-head self-attention mechanism and a feed-forward neural network. Now, what is multi-head self-attention? Basically, this self-attention mechanism allows the transformer to focus on different parts of input sequence at different times, capturing important relations between the words or characters. And this is done by generating a set of attention weights for each position in the input sequence. These weights indicate how much attention the transformer should pay to each position when processing a particular word or character. Next comes feed-forward neural network. Now, this feed-forward neural network is a standard multi-layer perceptron which takes the output of self-attention mechanism and processes it through the series of fully connected layers. And this helps the transformer learn more complex patterns in the input sequence, such as syntactic and semantic relations between the words. Now, this transformer also uses positional encoding to represent the order of words or characters in the input sequence, as it does not use a recurrent or convolutional architecture. This allows the transformer to capture long-range dependencies in the input sequence. So to summarize this, we can say transformer architecture is a neural network designed for NLP tasks that uses multi-head self-attention and feed-forward neural network to process sequences of words or characters efficiently, capturing the relations between them. Next comes attention mechanism. Now, this attention mechanism is a key component of transformer architecture in natural language processing, which allows a model to focus on different parts of input sequence when processing it. The goal of attention is to determine which part of the input are most relevant to the task at hand. To understand attention, let us consider a simple example. Imagine you are reading a sentence and need to identify the subject of sentence. You would likely focus on the beginning of the sentence where the subject typically appears. So attention works in a similar way by selectively focusing on certain parts of the input sequence. This attention mechanism in the transformer is implemented using a self-attention technique. Self-attention means the model attends to different parts of the same input sequence rather than attending to different sequences. Now it has key, query and value. So to compute this attention, input sequence is first divided into three parts, which are keys, queries and values. And these values are derived from the input sequence using a set of learned linear transformation. We have a dot product attention, that is to compute the attention weight for each position in the input sequence. The model takes the dot product of the queries and the keys, and this dot product is then scaled by the factor of 1 square root dk. That is, dk is the dimensionality of the key. And this helps to prevent the attention weights from becoming too large. Then we have a softmax function, that is a result of dot max. Attention is passed through a softmax function which converts the dot products into a probability distribution over the input sequence. This distribution represents the attention weights for each position in the input sequence. Then we have a weighted sum. So finally, this attention mechanism computes a weighted sum of the values using the attention weights generated in the previous step. So this weighted sum represents the output of attention mechanism for the current position in the input sequence. So to summarize all this, we can say that attention mechanism is a technique used in NLP model including transformers that allows them to selectively focus on different parts of input sequence and processing it. And this is achieved by generating attention weights that represent the importance of each position in the input sequence and using these weights to compute the weighted sum of values which represent the output of attention mechanism. Now next comes pre-training and fine-tuning LLM. Basically, this pre-training and fine-tuning are two key concepts in the development of powerful NLP models, particularly transformer-based models like BERT, GPT and Roberta. These techniques allows model to learn from large language or the large amount of data and adapt to specific NLP tasks. Now, what is understand by pre-training? Basically, pre-training is the process of training a large language model on a huge amount of text data before it is applied to any specific NLP task. The idea is to have the model learn general language patterns and features that are useful for the wide range of tasks. For example, BERT, a popular pre-trained transformer-based model, is trained on a massive corpus of text using a combination of two tasks, that is a masked language modeling and next sentence prediction. In the masked language modeling, the model is trained to predict masked tokens, that is the words or the subword units in a sequence. And this task helps the model learn contextualized representation of words, as it needs to understand the context to predict the masked tokens correctly. In next sentence prediction, the model is trained to predict whether a pair of sentence is likely to appear consequently in a text. And this task helps the model learn coherence and the relation between the sentences. Then comes fine-tuning. Now, this fine-tuning is the process of adapting a pre-trained model to a specific NLP task by training it on a task-specific data. The pre-trained models is used as a starting point, and the model's parameters are further optimized for the specific task. For example, to apply BERT to the sentiment analysis task, you would take the pre-trained BERT model and fine-tune it on a data set of text and corresponding sentiment labels. So during fine-tuning, the model parameters are adjusted to better classify the sentiment of text. This fine-tuning allows the pre-trained model to learn task-specific features and achieve good performance on a wide range of NLP tasks without the need for vast amount of task-specific data. So to summarize this, we can say pre-training is the process of training a large language model on a large corpus of text data, while fine-tuning is the process of adapting a pre-trained model to a specific NLP task by training it on a task-specific data. And these techniques allows model to learn general language patterns and features that are useful for the wide range of tasks while still being able to adapt to specific tasks with relatively little task-specific data. Next comes context window. In natural language processing, a context window refers to the portion of text surrounding a specific word or token that is considered when processing that word. The context window helps the NLP model understand the word's meaning and relation with other words in the sentence. For example, imagine you are trying to understand the meaning of the word happy in a sentence. So here the context window would consist of the word surrounding happy. So if the sentence is I am happy today, the context window for the word happy would include the words I am today and I am happy. Now the size of this context window can vary depending on the task in the model. In some cases, only a few words before and after the target word are considered, while in others the model might look at a much larger context. So in transformer-based models such as the BERT and GPT, the context window is dynamic and includes all the tokens in the input sequence. This is possible because transformer uses self-attention, which allows the model to attend to different parts of input sequence simultaneously. So to summarize this, we can say context window refers to the portion of text surrounding a specific word that is considered when processing that word. The context window helps the NLP model understand the word's meaning and relation with other words in the sentence. In transformer-based models, the context window is dynamic and includes all the tokens in the input sequence. Next comes masked language modeling. Now, this masked language modeling is a training technique used in transformer-based models such as the BERT, Roberta, and GPT-3. The goal of masked language modeling is to train the model to predict masked or hidden words within a sequence of text. And this allows the model to learn contextualized word representation, which are crucial for downstream natural language processing tasks. So during masked language modeling training, a fraction of the tokens in a given input sequence are masked or replaced with a special token. The model is then asked to predict the original token based on the context provided by the remaining unmasked tokens in the sequence. For example, consider the following sentence. The quick brown fox jumps over the lazy dog. So if we apply masked language modeling, we might randomly mask a word such as jumps and feed the modified sentence, that is quick brown fox mask over the lazy dog to the model. Now this model's task would be to predict this masked word jumps based on the context provided by the remaining unmasked words. And this process is repeated for the large number of masked tokens across a diverse set of text. As the model is trained on a vast corpus of text within vast words, it learns to understand the context and relation between the words, allowing it to effectively predict masked tokens in a variety of contexts. So to summarize this, we can say masked language modeling is a training technique used in transformer-based models where the fraction of tokens in a sequence are masked, and the model is asked to predict the original token based on the provided context. This allows the model to learn contextualized word representation, which are crucial for downstream NLP tasks. Next comes AutoRegressive language modeling. Now, this AutoRegressive language modeling is a training technique used in transformer-based language models such as GPT-3 and its predecessors. The goal of AutoRegressive language modeling is to train the model to predict the next word in a sequence based on the words that came before it. And this allows the model to generate coherent and contextually appropriate text. So during AutoRegressive language modeling, the model processes the input text sequentially, predicting each word one at a time based on the words that came before it. The training process starts with the first word of input sequence and continues until the end of the input. For example, given the text, the quick brown fox, the model would predict the first word the, then use the predicted word the along with the following words quick brown fox to predict the second word quick, and so on until the entire input sequence has been generated. The model is trained to maximize the likelihood of the entire input sequence, and to achieve this, it continuously updates its internal representation called the hidden states based on the input text it has processed so far. And these hidden states, along with the learned attention mechanism, allow the model to maintain context and dependency across the entire input sequence. So to summarize this, we can say AutoRegressive language modeling is a training technique used in transformer-based models where the model sequentially predicts each word in a sequence based on the words that came before it. And this allows the model to generate coherent and contextually appropriate text. AutoRegressive language modeling is the basis for generative language models like GPT-3, which are able to produce human-like text. Next comes tokenization. Now, this tokenization is the process of breaking down a larger piece of text into smaller meaningful units called tokens. So in natural language processing, tokenization is a crucial step because it prepares text data for further analysis and modeling. In NLP, tokens can be words, subwords, characters, or any other unit that represents a meaningful element within a text. The choice of tokenization depends on the specific NLP task and the properties of the input data. Now, this tokenization would include some steps like text preprocessing. So this step will involve cleaning and preparing the text data for tokenization. It typically includes tasks like removing special characters, punctuations, and numbers, converting text to lowercase, and handling text normalization. Then comes tokenization. So after preprocessing, the text is split into tokens. So in most NLP tasks, words are the primary tokens and the text is split into individual words. However, subwords, example using byte pair encoding of word pairs or characters, can also be used as token depending on the task requirement. Then we will have tokenization representation. So these resulting tokens are often represented as integer, which allows them to be fed into the machine learning models. So popular word tokenization libraries like NLTK, that is a natural language toolkit, uses a mapping of words to integers known as vocabulary. Subword tokenization libraries like byte pair encoding and word piece use a variable length vocabulary of subwords. So tokenization is an essential step in NLP tasks because it helps to break down complex text data into smaller manageable units that can be processed by algorithms and models. It also helps to standardize the input data, which is crucial for training machine learning models. So to summarize this, we can say tokenization is the process of breaking down a larger piece of text into smaller meaningful units called token. In NLP, tokens can be words, subwords, or characters. The goal of tokenization is to prepare text data for further analysis and modeling by breaking it into manageable units. Next comes embedding layer. Now this embedding layer in natural language processing is a technique used to represent words or other tokens as dense vector of real number. And these dense vectors are learned during training and capture the semantic and contextual relation between the words. Embedding layer is a crucial component of many NLP models as it enables the models to process the text data effectively. The embedding layer is used to convert discrete tokens into continuous dense vector, making them suitable for processing by the machine learning models. These dense vectors capture the relation between the words, allowing the model to learn contextualized representation of words. For example, in a word embedding model, each word in the vocabulary is assigned a unique vector representation. So words that are semantically similar, such as the king and queen, will have a vector representation that is also similar in high dimensional space. So this embedding layer is typically implemented as a matrix where rows corresponds to unique tokens in the vocabulary and columns represent the dimensions of the dense vector representation. The matrix is learned during training and its size is determined by the number of dimensions in the dense vector representation and the size of vocabulary. So to summarize this, we can say embedding layer is a technique used to represent words or other tokens as dense vector of real number. It is a crucial component of many NLP tasks as it enables the model to process text data effectively by converting discrete token into continuous dense vectors that capture the semantic and contextual relations between the words. This embedding layer is learned during training and helps the model learn contextualized word representation. Next comes positional encoding. Now this positional encoding is a technique used in transformer based model such as the famous BERT, that is a bidirectional encoder representation from transformer architecture, to provide the model with information about the relative or absolute position of each token within a sequence. And this information is crucial because the order of words in a sentence is essential for understanding its meaning. In transformer-based model, the input sequence is processed sequentially by the model layers. However, the model itself does not inherently retain the positional information of this input sequence, as the processing is done through a attention mechanism that operates on the learned representations of the token. So to address this, positional encoding is added to the learned embeddings before they are fed to the transformer layers. And this encoding provides the model with information about the position of each token in the sequence, which is crucial for understanding the meanings of sentences. Basically, there are two types of positional encoding. First is the absolute positional encoding. Well, in this method, a fixed sinusoidal signal is added to the learned embeddings to represent the absolute position of each token in the sequence. The sinusoidal signals capture the relative distances between the token, allowing the model to learn the positional information. Then we have a learned positional encoding. And well, in this method, a learnable vector is added to the learned embeddings for each token. These learnable vectors are learned during training and capture the positional information in a more flexible way than the absolute positional encoding. So both types of positional encoding ensure that model has access to the positional information of input sequence, allowing it to process the input in the correct order and understand the relation between words in a sentence. So to summarize this, we can say positional encoding is a technique used in transformer based models to provide the model with information about the position of each token within a sequence, and this information is crucial for understanding the meaning of sentence, as the order of words plays a significant role in NLP. So this positional encoding is added to the learned embeddings before they are fed into the transformer layers, ensuring that the model has access to the correct positional information. Next comes layer normalization. Now this layer normalization is a technique used in deep learning models, particularly in NLP and computer vision, to improve the stability and generalization of the training process. It is a form of normalization that operates on hidden layer outputs within a neural network. The main idea behind layer normalization is to normalize the activations of a layer before they are fed into the next layer. And by doing so, it helps to stabilize the learning process and improves the model performance. This layer normalization is applied to the output of each neuron within the layer. Specifically, it computes the mean and standard deviation of the activation across the neurons in a given layer and then scales and shifts the activation to have zero mean and unit variance. And this rescaling helps the model to focus on learning the important features without being overwhelmed by large or small activation. It has a few key steps. First, it normalizes the activation of given layer by computing their mean and standard deviation. Then subtract the mean and divide by standard deviation to standardize the activation. Then scale the standardized activations using a learnable scalable factors denoted by gamma and a learnable shift factor denoted by beta. So these learnable parameters allow the model to adjust the normalization process during training. Layer normalization can be applied within a single forward pass of the network and is typically applied after the nonlinear activation function in a layer. So to summarize this, we can say layer normalization is a technique used in deep learning models to normalize the activation of the layer before they are fed to the next layer. It helps to stabilize the learning process and improve the model performance by standardizing the activation and allowing the model to focus on important features. The normalization is achieved by computing the mean and standard deviation of the activation and scaling and shifting them using learnable parameters. Next comes dropout. Now this dropout is a regularization technique used in deep learning models to prevent overfitting, which occurs when the model memorizes the training data and performs poorly on the unseen data. So overfitting can lead to poor generalization, meaning the model won't perform well on the new unseen data. So this dropout works by randomly dropping out a fraction of the neurons during training. And this is done by multiplying the outputs of neurons by a dropout probability, typically a value between 0 and 1. So when the dropout probability is 0.5, for example, half of the neurons will have their output set to 0 during each training iteration. So we have some key benefits of dropout. First is the regularization. So by randomly dropping out neurons, dropout forces the model to learn multiple representation of data as different subsets of neurons are used for each training iteration. And this effectively increases the model complexity and leads to a more robust and generalized solution. Then we have computational efficiency. So this dropout is computationally efficient because it is implemented by simply multiplying the outputs of neurons by a dropout probability. No additional computations are required and the dropped out neurons have no effect on the forward pass of the network. That it is easy to implement. So dropout is easy to implement and can be applied to most deep learning models including neural network, recurrent neural network and CNN. So during inference, dropout is not applied. Only the average activations of the surviving neurons are used, which ensures that model is not overly dependent on any single neuron and allows for a more robust and generalized solution. So to summarize this, we can say dropout is a regularization technique used in deep learning models to prevent overfitting by randomly dropping out a fraction of neurons during training. And this forces the model to learn multiple representation of the data, leading to a more robust and generalized solution. So this dropout is computationally efficient, easy to implement and can be applied to a wide range of deep learning models. Next comes beam search. Now this beam search is a search algorithm used in NLP and other applications to find the most likely solution from a set of candidate solutions. It is particularly useful in tasks where the goal is to find the best sequence of elements such as in language modeling, machine translation and text summarization. The basic idea behind beam search is to maintain a set of candidate solutions called a beam and iteratively expand each candidate solution by considering the next element in the sequence. The candidate solutions are then ranked based on their partial score and the best solution. Typically, the top case solutions are selected to form the next iteration's beam. So let's take a simplified example. First, it has initiation. So at the beginning, the beam consists of a single candidate solution, usually the starting element of the sequence. Then it has expansion. So for each candidate solution in the beam, generate a set of candidate extensions by considering the possible next element in the sequence. Then we have a scoring. So you will assign a score to each candidate extension based on its likelihood or relevance, which can be computed using a pre-trained language model or a scoring function. Then we have a selection. So where you will rank the candidate extension based on their scores and select the k best solutions to form the next iteration beam. And this k is called the beam size. Then we have pruning. So if necessary, prune the beam to maintain a fixed size, discarding the lowest scoring solution. Then we have a termination. That is, we will repeat all the steps from expansion, scoring, selection and pruning until a termination condition is met, such as reaching a maximum sequence length or finding a complete sequence. So the key idea behind beam search is to maintain a set of candidate solution and iteratively expand them based on their scores. This allows the algorithm to explore a large space of possible solutions while maintaining a manageable set of candidate solutions. So by adjusting the beam size, you can control the trade-off between the accuracy and computational efficiency. So if we have a larger beam size, it will likely lead to more accurate solution because it will also increase the computational cost. So to summarize this, we can say beam search is a search algorithm used in NLP and other applications to find the most likely solution from the set of candidate solutions. It maintains a set of candidate solutions and iteratively expands them based on their scores. This allows the algorithm to explore a large space of possible solutions while maintaining a manageable set of candidate solutions. This algorithm can be tuned by adjusting the beam size, balancing accuracy and computational efficiency. Next comes greedy search. Now this greedy search is a simple and straightforward algorithm used in optimization problem to find the solution by making the locally optimal choice at each step. The idea is to make the best choice at each stage without considering the impact of these choices on the overall solution. So while greedy solution is computationally efficient, it does not guarantee the global optima as it does not consider the long-term sequences of the choices made. Basically, it is also having an initialization where we will start with the initial solution which can be randomly chosen or based on some heuristic. Then we will have selection. So that is at each step you will choose the local optimal solution from the available solutions. And this choice is made based on the scoring function that assigns a score to each available option. The option with the highest score is selected. Then we have update, where we will update the current solution by incorporating the selected choices. And finally, we have termination, where we repeat the selection and update until the termination condition is met, such as reaching a maximum number of iterations of finding the solution that satisfies certain criteria. So let's take a simple example to help illustrate the concept. Imagine you are trying to find the shortest path between two cities on a map. You could use a greedy search algorithm that chooses the road with the shortest distance at each step without considering the overall distance of entire path. So while this approach is simple and efficient, it may also not always lead to the shortest path. For example, if the map has roads with one-way traffic, the greedy search may choose a sequence of one-way roads that ultimately result in a longer path than a route with a few longer two-way roads. So to summarize this, we can say greedy search is a simple optimization algorithm that makes locally optimal solutions at each step without considering the long-term consequences on the overall solution. It is computational efficient but may always not lead to the optimal or the global solution or the global optimal. Next comes the BERT, that is the bidirectional encoder representation from transformers. Now this BERT is a popular deep learning model used in NLP tasks. It is a type of transformer based model that learns powerful representation of text by training on a large corpus of text data. So imagine BERT as very intelligent text understanding machine that has been trained to understand the meaning of words in a sentence and the relation with other words in a sentence. And this understanding allows BERT to perform various NLP tasks such as question answering, text classification, and language translation with high accuracy. The key innovation in BERT is its training strategy. So unlike previous NLP models, the BERT is pre-trained on a massive amount of unlabeled text data such as books, news articles, and web pages using a technique called pre-training. Now this pre-training helps BERT learn general language patterns and relations between the words that are useful for the wide range of NLP tasks. So after pre-training, BERT is fine-tuned on a specific NLP task by adjusting the few model parameters and training it on a labeled dataset for the task. And this fine-tuning process allows BERT to adapt to specific tasks while retaining its general language understanding. So to summarize this, we can say BERT is a transformer-based deep learning model that has been pre-trained on a large corpus of text data. It has a powerful ability to understand the meaning of words and the relations in a sentence, making it useful for the wide range of NLP tasks. So by pre-training and fine-tuning, BERT can learn general language patterns and adapt to specific tasks with high accuracy. Next comes GPT. That is generative pre-trained transformer. Now this GPT is a type of deep learning model that is closely related to BERT. It is also a transformer based model, which means it uses the same architecture as BERT but is primarily used for generating new text rather than understanding existing text. So just like BERT, GPT is trained on a large corpus of text data to learn powerful representation of words and their relations. However, instead of fine-tuning for specific NLP tasks, GPT is fine-tuned for text generation tasks such as language translation, text completion, and even creative writing. So imagine GPT as a text completion machine that has been trained on a vast amount of text data. So given a partial written text, GPT can generate a coherent and contextually appropriate completion for that sentence. And this is possible because GPT has learned to understand the relations between the words, phrases, and sentences, and it can use this knowledge to generate new text. So the main difference between the BERT and GPT is their focus. BERT excels at understanding and processing existing text, while GPT excels at generating new text. Both models are transformer based, share many similarities in the architecture, but GPT is specifically designed and fine-tuned for text generation tasks. So to summarize this, we can say GPT is a transformer-based deep learning model primarily used for text generation tasks. So like BERT, it is pre-trained on a large corpus of text data, but it is fine-tuned for text generation, allowing it to generate coherent and contextually appropriate text given a partial input. GPT excels at tasks such as the language translation, text completion, and creative writing. Next comes zero shot, one shot, and few shot learning. Now, the zero shot, one shot, and few shot learning are the techniques used in machine learning to perform tasks without the need for extensive training on the labeled data for each specific task. These techniques leverage pre-trained models and transfer learning to adapt to new tasks with minimal additional training. First, zero-shot learning. Now, in zero-shot learning, the model is trained on a general-purpose dataset, say ImageNet for the computer vision, and is not exposed to any data from the target task, that is a new unseen object during training. So instead, the model is evaluated on the target task using a set of textual description or attributes, example furry, brown, that describes the object in a task. The goal is to learn a mapping between the textual description and the objects without ever seeing the image of the objects during training. So imagine a zero-shot training model for the object classification. The model is trained on ImageNet and is not exposed to the images of new animal species during training. However, it is evaluated on a new set of animal species using textual description, example lion, cheetah, giraffe. So here the model learns to classify the new animal species based on the textual descriptions without ever seeing images of these animals during training. Then comes one-shot learning. Now in the one-shot learning, the model is exposed to a small number of examples, typically one of the target tasks during training. The goal is to learn a mapping from the few examples to the target task. So imagine a one-shot learning model for object classification. The model is trained on ImageNet and then exposed to a single image of a new animal species during training. The model learns to classify the new animal species based on the simple example and its similarity to previous seen images. Then we have few shot learning. Now in the few shot learning, the model is exposed to the small number of examples of the target task during training. The goal is to learn a mapping from the few examples of the target task. So imagine a few shot learning model for object classification. The model is trained on ImageNet, then exposed to few images of the new animal species during training. So the model learns to classify the new animal species based on these examples and their similarity to previous seen classes. So to summarize this, we can say zero-shot learning, one-shot learning, and few-shot learning are the techniques used in machine learning to adapt to new tasks with minimal additional training. These techniques leverage pre-trained models and transfer learning to learn mappings between the textual description or examples and target tasks. Zero-shot learning does not use any data from the target task during training. One-shot learning uses a simple example and few-shot learning uses a small number of examples. Next comes transfer learning. Now this transfer learning is a technique used in machine learning to leverage the knowledge learned from solving one problem to help solve a different but related problem. So in the context of large language model, transfer learning involves using a pre-trained large language model to perform a specific task without the need for extensive retraining. So imagine the large language model as a person who has learned to speak multiple languages. So the transfer learning with large language model is like using this multilingual person to learn a new language by fine-tuning the pre-trained model on a smaller data set in the target language. And this allows the model to adapt his knowledge to a new task without starting from the scratch. So in the context of large language model, the transfer learning is crucial because pre-training a large language model on the large corpus of text data is computationally expensive and requires vast amounts of labeled data. So by leveraging pre-trained large language models and using transfer learning, Researchers can adapt these models to perform a wide range of NLP tasks with fewer resources. For example, a pre-trained LLM can be fine-tuned on a smaller data set of news article to perform a sentiment analysis task, that is positive, negative, or neutral. So the model has already learned general language patterns during pre-training. So fine-tuning on a small data set allows it to adapt to the specific task of sentiment analysis. In simple words, transfer learning is a way of using a pre-trained LLM to perform a new task by adapting the model to the specific problem without starting from scratch. And this allows researchers to leverage the knowledge learned from solving one problem to help solve a different but related problem, saving time and resources. Next comes fine-tuning hyperparameters. Now this fine-tuning a pre-trained LLM involves adjusting the model's parameters to adapt it to specific tasks. Hyperparameters are values that control the training process and are set before training begins. So when fine-tuning a large language model, you adjust these hyperparameters to optimize the model performance on the target task. So imagine the chef, that is a pre-trained large language model, who has a recipe for making delicious cake, that is a pre-training process. Now the chef's recipe includes ingredients, that is a model architecture and pre-training data, cooking methods or the pre-training algorithms, and cooking items or the learning rate. So this fine-tuning hyperparameters are like chef's utensils or mixing bowls, measuring cups, and baking sheets. These utensils are not a part of original recipe, but they help the chef adjust the recipe to suit the desired outcome. So in the context of fine-tuning a large language model, we use some common hyperparameters like learning rate, which determines how quickly the model adjusts its parameters during training. Higher learning rate allows the model to learn faster but may lead to overshooting the optimal solution. Lower learning rate is more conservative but may require more training steps to converge on an optimal solution. So imagine the learning rate as the speed at which the chef adds ingredients to the mixing bowl. Then we have batch size. Now this determines the number of training examples processed at once. So if we have a larger batch size, it allows the model to learn from more data in each iteration but may require more memory. So imagine the batch size as the number of ingredients the chef measures and adds to the mixing bowl at once. Then we have number of training epochs, which determines the number of times the model will process the training data. So the more epochs, the more times the model will adjust its parameter. So imagine the number of training epochs as the number of times the chef stirred the batter in the mixing bowl. So by adjusting these and other hyperparameters, you can fine-tune the pre-trained large language model to perform a specific task more effectively. And this process of adjusting hyperparameters is often an iterative process involving training, evaluation, and adjustment until the model performs optimally on the target task. Next, we have evaluation metrics, that is the ROUGE, BLEU, and Perplexity. Now, these evaluation metrics are the tools used to assess the quality of the large language model when performing a specific task. These metrics help researchers understand how well the model is performing and identify the areas for improvement. In the context of large language models, three common evaluation metrics are ROUGE, BLEU, and Perplexity. First comes the ROUGE, or the recall-oriented understudy for gisting evaluation. Now this ROUGE is used to evaluate the quality of generated text, particularly in the machine translation task. It compares the generated text to the original text by calculating the overlapping n-grams between the generated text and the reference text. So imagine this ROUGE as a tool that counts the number of words that match between the generated text and the original text. Then we have a BLEU, or the bilingual evaluation understudy. Now this BLEU is also used to evaluate the quality of generated text in machine translation task. It calculates the weighted average of n-gram precision score up to 4 grams between the generated text and the reference text. BLEU scores range from 0 to 100 with higher scores indicating better translation. So imagine this BLEU as a tool that checks how closely the generated text matches the original text by comparing overlapping n-grams. Then we have Perplexity. Now this Perplexity is a measure of model's perplexity or the difficulty when generating text. If we have a lower Perplexity, it indicates the model is more likely to generate the input text. Perplexity is often used to evaluate language models on the language modeling tasks such as predicting the next word in a sequence. So imagine this Perplexity as a measure of how well the model can predict the next word in a sentence. So lower Perplexity means the model is more likely to generate the correct word. So these evaluation matrices are important for researchers because they provide a way to compare the model of different models and track improvements over time. They help ensure that LLM is producing high quality, coherent, and accurate output for the specific task it is performing. Next comes ethical consideration. Now, this ethical consideration are important when working with large language models because these models has the potential to impact society in various ways. It is crucial to be mindful of these ethical concerns and take steps to address them. So, some key ethical considerations can include bias. We know that LLM are only as unbiased as the data they are trained on. If the training data contain biases, so these biases can be perpetuated by the model. It is important to ensure that the training data is diverse and representative to mitigate the risk of biased output. So imagine a language model being trained on a data set that predominantly feature articles written by male authors. So if the model is not aware of female author and their contribution, it may generate biased answers that favor male perspective. Then we have privacy. Now, these large language models can be used to generate text based on user input, such as the questions or the prompts. It is essential to ensure that user privacy is protected, especially when personal information is involved. So, imagine the language model being trained on data set that includes personal information such as medical records. So, if this information is exposed or used inappropriately, it could have serious privacy implications for individual. Then we have fairness. Now, this large language model should be designed to treat all users fairly, regardless of their race, gender, nationality, or other personal characteristic. And it is important to consider how the model may be used and ensure that it does not perpetuate unfair or discriminatory practices. So imagine a large language model being used in a job application process that generates text describing a candidate's qualification. So if the model is biased against certain groups, it could perpetuate discriminatory practices and negatively impact job prospects for those individuals. Then we have transparency. So it is important to be transparent about how the model was trained, its capabilities and its limitations, and this helps user understand the model's output and make informed decision about when and how to use it. Imagine a language model being trained in a news article. So if the readers are not aware that article was generated by an AI model, they may not be able to critically evaluate the information presented. Then responsibility. So researchers, developers and users have a responsibility to use large language model ethically. This includes being aware of the potential consequences of the model's use, striving to mitigate negative impacts and promoting responsible use through education and guidelines. And by mindful of these ethical considerations and taking steps to address them, we can help ensure that large language models are developed and used in a responsible and ethical manner. Thank you.